Okay, so this is our review on exponential and logarithmic functions, and then we're also going to do a little review of solving exponential and logarithmic functions. So we have the definition of exponential functions, right? All exponential functions, or their parent function, can be written in the form of y equals a times b to the x, okay? Where y equals b to the x would be thought of as the parent function. The variable is in the exponent position. A is thought of as the vertical stretch or shrink factor. We refer to b as the base, and b has to either be greater than 1 or between 0 and 1, but it cannot be equal to 0 and it cannot be equal to 1. And here's why. If we think about b being equal to 1, like let's say that we had y equals 1 to the x power. Well, for any real number that we substitute in for x, we would just end up with 1. So this just ends up being a horizontal line. Okay. If b were negative, like let's say we let b be negative 2, well, if we substituted, let's say, positive 1 in for x, we would get y is equal to negative 2. And then if we substitute positive 2 in for x, negative 2 squared is positive 4. And then if we substitute 3 in for x, negative 2 raised to the third power is negative 8. So the y values would kind of oscillate back and forth between positives and negatives. Okay, so that just won't work. And then if b were equal to 0, okay, 0 raised to 1, 2, 3, 4, right? Any positive real number is just going to be 0. And 0 to the 0th power is undefined. And then if we thought about trying to substitute negative values, like if we thought about substituting negative 1 in for x there, we would end up with 1 over 0 raised to the first power. If we substitute negative 2 in, that would be 1 over 0 raised to the second power, which those values are undefined. So if 0 is the base, the graph of that is actually just a horizontal line that's only defined for x strictly greater than 0. Okay, so basically our base has to be, for exponential functions, the base has to be between 0 and 1, or strictly greater than 1. Okay, so you guys have probably also heard people, anytime something grows quickly, they say that it's growing exponentially, it's increasing exponentially, and that's just not always the case. There's different, like something can increase at a steady rate where it's more linear, so it's just things that grow quickly do not always grow exponentially or decrease exponentially, right? If something is decreasing or decaying. So if we think about this scenario that I've given you guys about my nephew Jonas, who has saved up, he's 3, and let's think he's saved up his money and now has $100 that he's decided to deposit into a savings account instead of storing in his dresser drawer. And this is a really smart decision on 3-year-old Jonas's part. But why? What's the difference between storing his money in his dresser versus a savings account at a bank? And the reason that it's a smart decision is because let's say he puts that $100 in his dresser drawer. A year from now, it's still just going to be $100. 2 years from now, it would still just be $100, unless he were actually adding money to it. But nothing's going to happen to it. There's no magic happening to make it grow. But if he puts his money in a savings account where it can earn interest, like let's say that this savings account that he put in earns like 2% interest annually. That means that if he puts his money in the account, then a year later, he will now have $102. And then a year after that, just assuming he himself is not putting any more money in, it'll be 2% more. And the year after that, 2% more than that. And as that amount gets larger and larger and larger, the amount that's added, right, that 2% of a larger amount, he's going to be making some money, more money than if he were to just put his money in the dresser drawer. So we would say then, if he put his money in the savings account, that his money would be increasing or exhibiting exponential growth. So the intuitive definition of exponential growth or decay is having a quantity or an initial amount, like in Jonas's case, that initial amount would be $100, that increases or decreases exponentially. A quantity that increases or decreases exponentially will grow or decay by a common percentage per period. In the example that I just gave you guys about Jonas, that initial amount, $100, would grow by a common percentage, which in this case would be 2%, right? If he earns 2% interest annually, and that period would be 1 year. So every year his money is going to increase by that common percentage of 2%. Okay? If we think of other examples of quantities that grow or decay exponentially, you can say populations can grow or decay exponentially, right? That bacteria can grow exponentially. Animals like rabbits will reproduce and their population will grow exponentially. If you have a medication in your system, the amount of medication in your system will decay exponentially, right? You talk about finding out or knowing the half-life of a medication, and then you can estimate how much of that medication, or calculate how much of that medication is in your system as time is passing from that initial dosage. Cell division, right? Cells are dividing, and so they're increasing exponentially. Use carbon-14 dating to determine, that's an example of exponential decay, but to determine how long something has been deceased. And those are some examples. Okay, so if we wanted to graph these two functions, they look very similar, right? We have y equals 2 to the x, and then we have y equals 2 to the negative x. So if we fill in the table for y equals 2 to the x, y equals 2 to the negative second would be 1/4. So that's the point negative 2 comma 1/4, and I could go ahead and plot that, or do my best to plot it. Then 2 to the negative first is 1/2. Plot that. 2 to the 0th is 1. 2 to the first. 2 squared. Okay, and then if I were to substitute 3 in for x, that would be 2 cubed is 8. And then I can draw the curve that passes through those points. Okay, so this is y equals 2 to the x. And then filling in the table for y equals 2 to the negative x. 2 to the negative x, that would end up being 2 squared, which is 4. That would end up being 2 to the first, which is just 2. Okay, so I think you guys can kind of see what's happening. 2 to the 0th is 1. Okay, that would be 2 to the negative first, which is 1/2. 2,1/4. Okay, and then I could also, if I substitute -3 in for x for this guy, then we'll get y is equal to 8. So the graphs have the same, oops, don't like that. The graphs have the same shape, but we can see that 2 to the negative x is the graph of 2 to the x, just reflected about the y-axis. And if we think about transformations from first semester, right, or not first semester, sorry, from pre-calc, then if you're multiplying the argument by a negative, that represents a horizontal reflection. Okay, so the domain of 2 to the x, it looks like, is all real numbers. And we could think about substituting any, so from negative infinity to positive infinity, you could substitute values in for x, and you would end up with a y value. The range, so let's think about the range. So as x is getting very large, y will just keep getting larger and larger and larger. And this is kind of thinking about end behavior, right? So as x approaches positive infinity, y, it seems like, is going to approach positive infinity as well, right? If we substitute 10,000, 10 million, a billion in for x, we get really, really large y values, and they would keep getting larger. But as x approaches negative infinity, so we're substituting really small values in for x, like negative 1,000, negative 10,000, negative 1 million, right? If we substitute negative 1,000 in, that would end up being 1/2 raised to the 1,000th power, which is a very, very small but positive number. And then if we substitute in negative 10,000 for x, it's 1/2 raised to the 10,000th power, and that's also a very, very small positive number. So, but even smaller than 1/2 to the 1,000th power. So it seems like our y values are getting small and they're approaching 0. So we could always use, we're not using limit notation the way I wrote it, but I could always say as x approaches, or if you take the limit as x approaches positive infinity of 2 to the x, that limit would be equal to infinity, or it actually doesn't exist, but we would say it would be equal to infinity. But the limit as x approaches negative infinity of 2 to the x would be 0. And when that limit exists, that means that there is a horizontal asymptote at that value. So there's a horizontal asymptote by definition at y equals to 0. And we can see now that the range is going to be from 0 to positive infinity. There's no real number that you could substitute in for x that would give you y equals to 0. Just numbers that are very, very close to it. The domain of 2 to the negative x is also all real numbers. The range is also 0 to infinity. Oops. The end behaviors flip though. So as x approaches infinity, it looks like y is approaching 0. Right? So the limit as x approaches infinity of 2 to the negative x would be equal to 0. So that means there's a horizontal asymptote also at y equals to 0. And as x approaches negative infinity, it looks like y is approaching positive infinity. Okay, so another way that we can write y equals 2 to the negative x is to think about this as 2 raised to the negative first power, then raised to the x power, right? That's a exponent rule property. And then we can write 2 raised to the negative first power is 1/2. Okay, where our base is 1/2. Our base b is 1/2. If b is between 0 and 1, then the graph is going to exhibit exponential decay. But if B, like here, B2 is B in this case, if B is greater than 1, then the graph will exhibit exponential growth. And we can see that in our two graphs here. I'm going to skip these. The main point is that exponential functions can be graphed using translations and transformations, just like other types of functions you've studied before. But let's look at the natural base e. So we'll see 2 and 10 as common bases for exponential functions and applications. But you'll also see the irrational number e, called Euler's number, after the mathematician Leonhard Euler. And it's also referred to as the natural base. And e comes from evaluating the expression 1 plus 1 over n to the nth power as n approaches infinity, right? So taking the limit of that expression as n approaches infinity, it seems like that value would be approaching 2.71827, which is approximately e, right? E is a transcendental number. It will not be the root of a polynomial, and it's kind of like pi. It's an irrational number. You can never memorize all of the digits of e. It's impossible, right? It has infinitely many non-repeating digits. Okay, but you should know that it's approximately 2.71. Okay, so we could graph e and e to the negative x, but basically for e to the x, e is positive. That's a positive base that's greater than 1. So that graph will exhibit exponential growth. And if we have that negative there, this is equivalent to having 1 over e raised to the x power. So 1 over e lies between 0 and 1. So this graph would demonstrate exponential decay. Okay, logarithmic functions. So note that exponential functions are one-to-one functions. If you remember from pre-calc, one-to-one functions means that every element from the domain corresponds to exactly one element in the range, and every element in the range corresponds to exactly one element in the domain. Every x has exactly one y, and every y has exactly one x. So remember last year when you guys studied inverse functions, for a function to have an inverse, it had to be one-to-one. So as long as a function is one-to-one, it has an inverse, and it is the inverse of another function. So let's graph to the x, which we already graphed. Just going to throw it on here quickly. Oops, not a line. Don't like that one either. All right, there we go. Okay, so this is y equals 2 to the x. Now, we know points that lie on y equals 2 to the x. Right, this is negative 2, comma 1/4. Let me make this a little thinner. Negative 2, comma 1/4. We had negative 1, comma 1/2. 0, 1, 1, 2, 2, 4, 3, 8. Now, if you remember, inverse functions have opposite domain and ranges, right? So if you have a function that has its own domain and range, then you know that its inverse function, the domain of its inverse function will be the range of that original function, and the range of the inverse function will be the domain of the original function. Right? Like if we had, let's say, I always like to draw the picture of the function machine. So let's say this is a function f, and then this is f inverse. Okay? If I were to input, say, 2 into f, and the output was 8, okay? If I take 8 and input it into f inverse, its output will be 2. The domain and the range flip-flop, meaning I know that if the point -2, 1/4 lies on the graph of 2 to the x, on its inverse function, there will be the point 1/4, -2. If -1, 1/2 lies on the graph of 2 to the x, on its inverse will be 1/2, -1. 0, 1 will now, on f inverse, or its inverse, will be 1, 0. And 2, 1, 4, 2, 8, 3. So this is the graph of the inverse of y equals 2 to the x. The thing is, can we find the equation? If you think back to last year when you were finding the equation of a function's inverse, right? You took the function, you switched the x and the y, and then you solved for y. But the thing is, y is in the exponent position. We can't use any properties of equality to isolate y. So what we're going to end up having to do is take the log base 2 of each side of the equation. We'll talk about properties of logarithms in a second. So we take the log base 2 of each side, which then this ends up being y equals 2 log base 2 of x. So if I call this, sorry, I just said this was y equals. So if this is f, that means that f inverse is the log base 2 of x. Logarithmic functions are the inverses of exponential functions. All right, here's the definition. You can always write a logarithmic equation in its equivalent exponential form or the other way around. So y equals to log base b of x if and only if x is equal to b to the y. Sorry, if and only if x is equal to b raised to the y power. So I like to draw these arrows, right? B raised to the y power has to be equal to x. So we can write these logarithms in their equivalent exponential forms, right? 2 cubed is equal to 8. That's an equivalent statement. 4 to the 1/2 is equal to 2. 7 raised to the -2nd power is equal to 1/49. And then we can rewrite these exponential statements in logarithmic form. So log base 8 of 64 is equal to 2. Another way to rewrite the square root, right, is 169 raised to the 1/2 power. So log base 169 of 13 is equal to 1/2. Log base 5 of 1/25 is equal to -2. And we can evaluate logarithms. So I like to think of it, okay, log base 6 of 36. So I go 6 to what power is equal to 36. So I almost rewrite it in its equivalent exponential form. That would be 2. 4 raised to what power is equal to 1/4? Well, that would be -1. 5 raised to what power is 125? 3. Okay, log base 10 is the common log, has its own button on the calculator. Log base e is the natural logarithm. So, and we use ln of x, and it has its own button on the calculator. So ln of x is the same as log base e of x. Okay, they're inverse functions of each other. Here's their characteristics and graphs. You guys need to know your properties of exponents, and you're expected to know your properties of logarithms. If you have questions about how they're kind of derived, it's all based on the properties of exponents, but I'm happy to go through them with you. Okay, so using properties to simplify. Well, log base 5 of 5 has to just be equal to 1, right? That's this property here. If you have the log base b of b is just 1, because 5 raised to the first power would give us 5. If you evaluate a logarithm at 1, it has to be equal to 0, because the base raised to the 0th power would give you 1. If you have a base raised to the log of the same base of something, then it's almost like the bases cancel out and you just end up with the argument. So in this case, we would have, for 10 raised to the log base 10 of 2 plus x, we just end up with 2 plus x. 3x minus 4. Okay. For this guy, we could use, I know Miss Walters calls it plog, so I call it plog as well, right? Where if you have log base b of m raised to the p power, you can pull that power out front. So if we were to pull the power out front here, we would have x squared times log of 10, which we know that log of 10, that's log base 10 of 10, is just 1. So this is actually just x squared. Oh, that actually is a property. That's this property over here. But it can be thought of as using plug as well. Okay, so then this would just be x plus 5, according to the property. All right, change of base formula is a way that you can evaluate logarithms without, so you can evaluate logarithms on your calculator by hitting math and then going, scrolling up to A, and then you can type in whatever the base is you want and the argument. But if you just want to use the log or the ln buttons to evaluate a logarithm, it doesn't matter. So if we want to evaluate log base b of m, you can take the log of it, doesn't matter what the base is, of m, over the log of, it just has to be the same base as in the numerator of b. So it's common to use, say, okay, this is log of m over log of b will give us the same as natural log of m over natural log of b. And we're going to use change of base formula in helping us to derive the derivatives of some of the functions of the logarithmic functions. Okay, so for solving exponential and logarithmic equations, we're going to be using all of the properties from above, but also one-to-one property, which says if you have the same base, so like if we have b to the x equal to b to the y, that means that x has to be equal to y. The exponents have to be equal. And if we have the log base b of x equal to log base b of y, that means the arguments have to be equal. X has to be equal to y. And the inverse property is really just writing or thinking about the equivalent exponential and logarithmic forms. Okay. So if we wanted to solve this simple exponential equation, it's really nice when we're able to use one-to-one property, but if you don't see using one-to-one property right away, that's okay. Like, we can actually write 81 as 3 raised to the 4th power, where then by one-to-one property, x has to be equal to 4. But if you didn't know that 3 raised to the 4th power is 81, that's okay. We could have also taken the log base 3 of each side of the equation, or rewritten this in its equivalent exponential form. Its equivalent logarithmic form. So the log base 3 of 81 is equal to x. And then log base 3 of 81 is 4. You type that into your calculator. Okay, so here we can actually use one-to-one property again. We can write 125 as 5 cubed. So then we have 7 minus x equals to 3. So negative x equals to negative 4. X must be equal to positive 4. Again. All right, we can write 16 as 1/2 raised to the negative 4th power. Yeah, because that would be 1 over 2 to the negative 4th. Or I'm sorry, that would be 1 over, 2 to the negative 4th, which would be 16, yeah. So then we have 4y equals to negative 4, y equals to negative 1. Okay. More complicated exponential equations. So 27 cannot be rewritten as 5 raised to some power. So we're going to take the log base 5 of each side of the equation, where we'll end up with y squared equals to log base 5 of 27, and y is plus or minus the square root of log base 5 of 27. So there's two solutions here, and this is how we represent the exact values, and then we could type it into our calculator to get the decimal approximation. So I hit log on my calculator and go up to A. So I type in log base 5 of 27. Oops, sorry, I should have done the square root of that. So we get plus or minus approximately 1.431. Okay, if we take the log base 4 of each side, we'll end up with 3x plus 2 equals to log base 4 of 71. And then if we subtract 2 and divide by 3, we'll have x is equal to the log base 4 of 71 minus 2 divided by 3. So that's the exact value. And then if we type that into our calculator, I get approximately 0.358. Okay, before we can take the natural log, here we need to divide by 4 on each side of the equation to isolate e to the x squared. 64 divided by 4, having a brain fart, 16, that's right. So then x squared is equal to ln of 16. So x is equal to plus or minus the square root of natural log of 16. So x is approximately plus or minus the square root ln 16. So we get plus or minus 1.665. Okay, we have a base of 10, so we can take the log base 10 of each side of the equation and isolate x. Okay, that's our exact value. Then we can type it into the calculator to get the approximation. Okay, so an exponential equation in quadratic form. Now notice that e to the 2x can be written as e to the x squared, where we can either factor this as is, or we could let u equal to e to the x. So do u substitution. So u squared minus 4u. I'm just replacing all the e to the x's. Plus 3 equals 0. And then that's factorable, right? Okay, so by zero product property, we'll end up with u is equal to 1 or u is equal to 3. Replacing the u with e to the x. E to the x equal 1, we could solve that by inspection. X must be equal to 0. And then we'll have x is equal to ln of 3, which is approximately 1.099. So 2 solutions. All right, solving simple logarithmic equations. Whenever I refer to them as simple, because for those ones we can usually use one-to-one property. So we can't use one-to-one property as is because we have this sum on the right side. But using one of our properties of logarithms, we can rewrite that as a single logarithm. So as x, the natural log of x times x plus 3, right? If we have a sum of logarithms that have the same base, we can rewrite as a single logarithm where we multiply the arguments. And then now by one-to-one property, x plus 3 has to equal to x squared plus 3x. Get 0 on one side of the equation. And that can factor. So x is equal to negative 3 or x is equal to 1. Okay, and we need to check, because notice that we're dropping the logarithm, so we need to check when we use the one-to-one property, or if we rewrite in the logarithm's equivalent exponential form, we have to always check for extraneous solutions. The domain for logarithm is from 0 to infinity, so we cannot evaluate logarithms at 0 or any negative values. So we need to double check that the answers we come up with or the solutions we find actually make sense in the original equation. Because notice we were able to drop the logarithm and that was just solving a quadratic equation. Well, quadratics have domains of all real numbers, but logarithms do not. So if we substitute negative 3 in for x up here, we're going to run into an issue here and here, right? We can't take natural log of negative 3 and we can't take the natural log of 0. So negative 3 is actually an extraneous solution. We cannot include it as part of our solution set. But one will work. So 1 ends up being our only solution. So if you're solving a logarithmic equation, make sure you are checking your solutions. All right, this next one we are unable, switch colors, we are unable to use one-to-one property, but we can rewrite it in its equivalent exponential form. So 4 to the negative second is equal to 5 minus 2x. So it's 1 over 16 is equal to 5 minus 2x. If I subtract 5, okay, I'm going to get negative 79/16 minus 2x. Sorry, equals to minus 2x. And if I multiply by negative 1/2 on each side of the equation, I'm going to end up with x is equal to 79/30. We need to double check that that will work. So think about substituting it back in. 5 minus 2 times 79/32 is positive. So that works. This is our actual solution. Okay, so we're not going to be able to use one-to-one property here, but before we can rewrite in exponential form, we need to rewrite that as a single logarithm. So log base 5 of x times x minus 4 equals to 1. So 5 raised to the first power is equal to x times x minus 4. And then we just have a quadratic. And we need to check for extraneous solutions. Negative 1's not going to work. Oops. Sorry. Negative 1's not going to work. But 5 will. Okay, these really aren't that much more complicated. Might not even go through all these. This is going to be 1. So we'll have log base 2 of 4x minus 1 equals to 2. If we add 1 over, okay, 2 cubed, oops, 2 cubed equals to 4x. So we get x is equal to 2. And 2 does work. Okay, rewrite as a single logarithm. So this is going to be e raised to the 4th is equal to x squared minus 2x. This is just a quadratic. Okay. So that cannot be factored. So we're going to actually have to use quadratic formula here. So x is equal to 2 plus or minus the square root of 4 minus 4ac all over 2a. Okay, so we get x is approximately, wish I had quadratic formula programmed into my calculator. Divided by 2. So I get 8.456 or negative 6.456. If we check, oops, this guy's not going to work. Only solution is 8.456. Okay? Alright, we'll do the last one. Okay, so rewriting this as a single logarithm, so log base 7 of 1 minus x times x. Oh, this isn't plus. Sorry. So because this is a difference of two logarithms with the same base, this will be log of 1 minus x over x plus 2. So now by one-to-one property, this is 1 minus x over x plus 2 equals 2x. We can multiply by x plus 2 on each side of the equation. So we get 1 minus x equals to x squared plus 2x. 0 equals to x squared plus 3x minus 1. Not factorable, so we have to use quadratic formula. So negative 3 plus or minus square root b squared minus 4ac all over 2a. So x is 303, or x is approximately 3. Okay, we need to double check this would work. This guy would not work. So here and here. But this, so approximately 0.303 is the only solution. Okay, so your guys' homework is 1 through 14, and then there is a homework